Okay, we are going to do part of Chapter 3 today through Section 3.1 of the textbook. This is where we start talking about functions of random variables and some geometric probability, and a lot of the homework problems that I've been giving have, at least of late, have had to do with some of the work that we're going to be doing today. So 3.1 is called Functions of Random Variables and Derived Distributions, and we are going to be following 4 important steps here to developing these derived distributions. And we're going to be talking about lengths of highway stretches here. So the first thing we're going to do is figure out, what is our random variable of interest. So we need to explain in words what the random variables are. Then we're going to identify, we're going to be working with joint probability density functions in this lecture. Identify the joint sample space. Then what we're going to do is determine the joint probability distribution over the sample space. And once we know what that is, we are going to determine the PDF, the CDF, and then anything else that we want. We could do, say, the expected value of some random variable x given a y value, or just the expected value of y, or the expected value, or the variance of x, and so on. And we're basically going to be doing this by determining what the CDF of interest is first, and then we'll take the first derivative to get the PDF. So I'm hoping that you remember that from some of your training, is that if I want to get, we know that when I want to get the CDF of a random variable, that's when we integrate from our lowest value of x up to some general value of x over the PDF. But that's not what we're going to be doing today. What we're going to be doing is we're going to figure out what our CDF is first, and then we're going to take the first derivative of it so that we can get the PDF, and then from the PDF we'll be able to use our formulas to get expected value and variance of whatever random variable we're interested in. So I know you've seen it before. We're just going to apply it in a little bit of a different way in this lecture. So let's start out with an example, pretty simple little example. Imagine that we just have a 1 unit length of highway, and I'm going to be using 1 mile as my unit length. And suppose that I've just got this, again, this is just 1 mile long. And randomly on this strip of 1 mile, we're starting out with 1 mile, and then we're going to extend it to S miles, as many as we want. And we've got an ambulance that just is regularly moving at any point along this 1 mile stretch of highway in a random way. It could be located anywhere randomly along this 1 mile. Whenever I use the word random, we're talking about a continuous uniform distribution. And then we also have an accident that can occur randomly along this 1 mile strip of highway. And what I want to do is figure out what is the PDF, the CDF, the expected value, and the variance of the distance that the ambulance has to travel to the scene of the crash. Therefore, we're talking about this distance d. I'm going to define it as a random variable d, which will be the distance from the ambulance to the crash. Now, because these can be located anywhere on this 1 mile, it's possible that the crash could be located over here, and that the ambulance is located over here. You understand? So we could have the different locations, one to the left of the other, one to the right of the other. I'm going to point that out. We are allowing U-turns on the highway, and as I said, we are independent and equally likely to occur anywhere on the highway. And this right here means that they are random. And the key word here is independent, meaning the location of the ambulance is independent of the location of the accident. All right, so those are our assumptions. So let's start out with step 1. Step 1 says define the random variables of interest. Right here. Let me keep up with my my notes here. I have some notes that I want to make sure I get to. Okay, so it says define the random variables of interest, and I am going to define x1 to be the location of the accident right here, and x2, oh, you know what? I don't really like, I noticed this here. That should be a little lowercase x1 there. And x2 is going to be the location of the ambulance at the moment of the accident. So again, this should be a lowercase x2. And then D, the travel distance between the two, that's going to be the absolute value between x1 and x2. Now, why is that? That's because it's possible that the actual accident here, which is x1, could be over here. So we certainly could have x1 over here, and we could have x2 over here, like down here on the... So if we're looking for the absolute value of the distance between them, distance is going to be positive, so I want the absolute value of the distance. Step 2 says, identify the joint sample space. So what I'm going to do here, I want to say everything? Yeah, I did on one other thing too. This is my random variable D. My specific values that D can be here are going to be for my, again, this is 1 mile long here, and this is 0 miles here. D can be anything between 0 miles and 1 mile. And again, it's a continuous random variable, so that equals part of the inequality doesn't really matter. Step 2 says, identify the joint sample space. This is really a pretty simple slide. I probably didn't need a whole slide for this. But the joint sample space means that, well, I'm working towards using a geometric probability. So kind of like if you remember when we did the stick cutting problem and we said that we could make, remember we could make 2 cuts on a stick, and we looked at the sample space there, and then we figured out the CDF for the probability that we could make a triangle. So this is not that different from that application. These are really should be like lower, these really should look like this. I'm not very happy with the way this came out here. Right there, x2. And we know that these are my random variables, and again, that x1 could possibly be over here, and x2 could be over here, and this is going to be my unit square. So x1 can be anything from 0 to 1 mile, and x2, same thing, can be anything from 0 to 1 mile. And what I'm going to do is I'm going to use, just like we did with the stick cutting problem, we're going to be mapping out some areas in here to figure out the probability functions for the random variable D that we're actually interested in. Okay, step 3 says, determine the joint probability density function over the sample space. Probably not, probably isn't super necessary for what I actually want to accomplish here, but it doesn't hurt to do this. So remember, whenever we have 2 random variables that are independent, that the joint probability density function, or mass function rather, if it was a discrete random variable, same thing, is just the product of the 2 marginal PDFs. So we know that for this particular problem from the previous slide, that, I'm going to save that, hang on a second, hang on to that just in case I need it again. So we have both of these are continuous uniform distributions. They are independent, and so these are the marginal distributions for x1 and x2. So the product of those marginals is going to be my joint probability density function. So another kind of simplistic application there. But now what we're going to do is we're going to use this joint PDF to figure out what the CDF is and answer some questions and find some quantities, all right? Now, I'm actually going to do it kind of backwards from what the slide says in this case, because I want to exploit this geometric unit square that we've got. So it says use the joint PDF to find the CDF, and I want to add this here, or use the CDF to find the PDF. So I'm actually going to use the second method here. But here we've got my 2 random variables, and again I'm going to keep pointing out that we could have x1 on the left and x2 on the right. We want to figure out what is the PDF of my random variable D. So remember what D is. D has been defined to be the absolute distance or difference between my 2 random variables right there. And that's what I said I'm going to do. I'm going to figure out the CDF first, and then what I'm going to do then I'm going to take the first derivative. So this doesn't look very good. I'm going to take d dd. This is the one means derivative and the other means my random variable value of my CDF here. And that's going to get me my PDF, and then from my PDF I can get the expected value and the variance. So there's two cases that I actually have to consider here. And those, as I've mentioned up here, is the first case where x1 is actually larger than x2. So remember, this is 1 mile, and what I've shown here is x1 larger than x2. So if I were to map out on this mile marker where x2 and x1 are, x1 is bigger than x2, but I also could have x2 bigger than x1. So I have both of these cases here. And that would mean that in this particular case, the distance between the two would be x1 minus x2. And then in this case, the distance between the two would be x2 minus x1. And that's the whole point of that absolute value equation right here for my random variable d. Okay? So now what I'm going to do is I'm going to go back to that unit square of the joint probability density function. I'm looking for one other thing here. Hang on a second. I am looking for, yeah, want to make sure I just had 4 steps. So this is going to be our last step, and then we can, we'll have the distribution values that we actually want. Okay, now right here, I've already done some pre-processing of my graph, but notice that I've got some colors here. I've got a green line here. Maybe I'll stick with the colors. That's probably a very good idea. I've got this green line here, and then I've got a blue line, and then I just drew the horizontal, or the line x1 equals x2, just kind of for perspective. All right. Okay. Now, again, this should be like a little lowercase. You don't mind me correcting my own slides here, I hope. This is 1 mile. I also think it slows me down, so it's probably good that I do this. Okay, here we have this. Now, as I said before, case 1, let me make sure I color code this exactly right. Case 1 is when x1 is to the right of x2. So which color is that going to be? Let me see here. Let me determine where that is exactly. So case 1, I'm going to be using green for right here. And as I said before, this indicates that my random variable x1 minus x2 equals to my random variable d. Now let's go ahead and develop case 1, and then I'm going to let you develop case 2 on your own, okay? Or at least I'll show you where it will be on the graph. Here's case 1. The first thing I want to figure out is what is my CDF for my random variable d. And that's going to be, as we know, the definition of it is the probability that d is less than or equal to a particular value of d. Now, since it's case 1, we're looking for x1 minus x2, right here, keep going, probability that x1 minus x2 is less than or equal to a particular value of d. So notice that I have these other tick marks here on the x and y axis. So this tick mark here is just going to represent this value of d, which could be the distance between the two, as is this one here, right? So what I want to do here is I want to plot this region right here. So if I just plug in a couple of values, so for example, if I plug in x2 is 0, which puts me right here, if x2 is 0, then x1 is going to have the value d. So that's going to be this point right here. And then I could plot another point as well. If I were to make x1 equal to 1, then x2 is going to be 1 minus d. So just the coordinates here to point out. This coordinate here, just to be clear here, is d and 0. And this coordinate right here is 1 and 1 minus d. And this is going to be 1 minus d here. And this value here is 1 minus d. So the whole point of this is I'm just trying to plot this region. So I've plotted the equality version here, x1 minus x2 equals d, and now what I want to know is what is the region such that these two are less than or equal to d. So just pick a point, pick 0, 0. If 0, 0 satisfies this equation, then I know that I'm looking for a region that goes this way, right? You know this from taking IEE 376, discrete operations research. And that's exactly the case. So if I plug in 0, 0, that's definitely less than a positive value of d. So I know that for this case, I need the region that goes this way here. And I also know that if I do case 2, I'm going to have a parallel line, but it's going to be on the other side of this x1 equals x2 line. So here is case 2, and again, remember with case 2, we're saying, well, x2 is the one that's the rightmost point, so x2 minus x1, that's going to equal my random variable d. And so for case 2, maybe I'll just kind of set this up here. We're going to do the same thing. We're going to say, what is the CDF of my random variable in this case? Again, is going to be the probability that d is less than or equal to d. I need both of these cases. In other words, I need both of them. And so this is going to be the probability now that x2 minus x1 is less than or equal to this little value of d, and then we can get 2 points and then draw the line there. So for example, if x1 is 0 here, then x2 is d, so that represents this point right here. This is 0 and d, and then this point up here, if I set x2 equal to 1, then I know that x1 is going to be 1 minus d here, so we'd have 1 minus d and 1. The point is I'm just trying to find 2 points that are on a line and then draw that line. Now I also need to know, well, what is this region? And again, I'm going to plug in 0, 0 here, and I'm going to see that if I do 0 minus 0, that's definitely less than or equal to d. So now I know for this case that I need the region this way here, right? Okay, so now my total, my probability that, let me write it in black here, the probability that d is less than or equal to this particular value is going to have to be the region shown by case 1 plus case 2. So I'm looking for basically the intersection of both of these. So this is just, the green is just that portion of the CDF that is case 1, the blue is that portion of the CDF that is case 2. So what I want, where is it here? Oh, I'll use a different color. I like this. This is what I'm trying to figure out, this region right here. So I'm going to take this green area here, divided by this 1 square mile, and that will give me the probability, it'll give me the CDF, so the probability that d is less than or equal to little d. So the easiest way to do that, though, is to simply recognize that I can get this whole green area here, right? This whatever, chartreuse green, is just this whole unit area, 1 times 1, minus these 2 triangles right here. Now those 2 triangles are exactly the same area. So if I do this, I'm working a little bit without a net here, okay? So I've got this area, and I've got this area. Okay. So let me just use my colors here. So this slash 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 area is f d of d. If I take this green area and I divide it by that 1 mile squared, right, 1 mile this way, 1 mile this way, that gives me an equation for fd of d. But the easier way to do that is to do the following. I know that this shaded area, that is just equal to 2 times this area. You like how this is not very fancy, but I just want to kind of point that out. So this green area, I'm sorry, it's 2 times that, it's 1 minus that, apologies. It'll be 1 squared minus 2 times that yellow area, okay? So let's just put this all together. We know that capital F d of d is going to be 0 whenever my random variable is less than 0, because we know that the range on it has to be between 0 and 1. And we also know that it has to be equal to, is this showing up? Yep, 1 whenever d is bigger than 1. So what we're interested in is what goes in here when my random variable is between 0 and 1. And I'm just going to take these two weird looking visuals that I made and create it, right? So here we go. So we're going to take the top part, this chartreuse green slashy stuff is actually 1 minus 2 times the area of either one of these triangles. So with just 1/2 base times height, so it's 1/2 base. Now the base, you can take either base if you want. This base here is going to be the area between d and 1. This is just 1 minus d, so we have 1/2 the base, which is 1 minus d, times the height, and the height here happens to be 1 minus d. So I'm going to have 1/2 the base times the height, which is also 1 minus d. And then this works out so that the CDF for d between 0 and 1 is then going to be 1 minus d squared. From that, now what we can do is we can go over here, let me make kind of a line, and now we can get the PDF by taking the first derivative, so I could call it, f prime of d. So I'm going to take the first derivative, let me just write it, d of f d of d. And when you do that, you're going to get, if you don't know if you remember how to do this much or not, but you're going to take the 2 and bring it down. So we're going to have a minus 1, bring the 2 down, times 2, times 1 minus d, now raised to the first power, times the minus 1 that's in there. And when I pull all of this together, it ends up being just 2 times 1 minus d. I'll rewrite that there. So that's my PDF right there. And that's good for 0 less than or equal to d less than or equal to 1. And then I'm going to let you show, all right, you do, because some of you probably need some practice with this, the expected distance then between two random points on this 1 mile line. So the expected distance between an accident and an ambulance that are independent and both randomly located on a 1 mile strip of street, the expected value works out to be 1/3 of a mile. And the variance works out to be 1/18, and that would be miles squared. And I want you to do that and verify that those values are correct. Now, what do we do? What if the strip of the road is not 1 mile, but what if it's 2 miles long? How does this change? So let's take a look at that, and then we're going to develop a general form for it. Okay? So same idea. I might have to come back to this. How does the problem change? I don't really like those wordings. How does the problem change? What do I mean by problem change? Really, if I had it to write over, I would say, what is the CDF and the PDF of the distance between the two accidents if we have a 2 mile distance long road here? So if I don't know why I wrote D prime there. If the road is, sorry about this. I haven't taught this in a while. I haven't caught all my other mistakes. So if the road is 2 miles long, how does this change? All right. So what we could do you could, in fact, you probably should do it. I mean, if this feels a little, if you feel rusty with probability, this is probably a great exercise is to walk through all of this. But if I follow my steps 1, 2, 3, and 4, I'm going to notice that I've got, let's see, if I drew my road, let's do it up here, right here. So now we have 0 miles, and now we have 2 miles. And now we're looking for an accident and an ambulance. And again, this could be X1 or X2. Either way, just to refresh your memory, we know that the joint probability density function for each of those locations, since they are independent, X1, X2, that's going to be a product of the marginal. So I'm going to write it down, and then we're going to see why it is this. We're going to have 1 over 4, and that would be for the location of my accident between 0 and 2 miles, and the location of my ambulance between 0 and 2 miles. So how do we get this? Well, remember that the marginals here, they're just continuous uniform random variables. So if we are allowed to have an accident between 0 and 2 miles, then if it's a continuous uniform, then this must be 1 over b minus a. And the marginal for x2 then must be exactly the same. And to get the joint probability density function, I just multiply them together. So that's where that came from. Don't really need that for anything else unless we're interested in computing probabilities of their location, but it's instrumental, I think, to go through this. Now, what I'm going to do, I could go through and I could develop everything just the way I did it on the previous 2 slides, but instead I'm actually going to use a variable substitution here to derive what the CDF, the PDF, the expected value, and the variance would be if we had a 2-mile strip of highway. So let me use another color here. I'm going to define a new random variable. I'm going to call it just d prime, okay? Just a new random variable. That's just going to equal 2 times d from the previous slide. So remember that d from the previous slide was defined to be the distance between the 2 accidents, between the accident and the ambulance. Now I'm just going to, and we know that the values on that random variable were 0 to 1. So now d prime is just 2 times d. It just could be twice as long, right? Okay, so now I'm just going to do what we learned about in 385, if you took 385 with me. Now we want to develop the CDF for d prime. So capital F, capital F of my new random variable d prime is just the probability that d prime is less than or equal to, right, a specific value of d prime. And now I'm just going to substitute in here, which is the same thing as the probability that 2 times my old d is less than or equal to d prime, which is the probability that my old random variable d is less than or equal to some specific value of d prime, divided by 2, and then we recognize this to be the CDF of my old random variable d, but we're going to evaluate it this time not at a little d, but at a value called d prime over 2. And let me see here. So just recall, I'm going to, from the previous slide, I want to write this down so you can remember it. So from the previous slide, this is what we determined capital F d of d was. That was 1 minus d squared for 0 less than or equal to d, less than or equal to 1, and of course it was equal to 0 when d was less than 0, and it was equal to 1 when d was bigger than 1. So now what we're going to do is we're going to take this function here, but wherever we see a d, we're going to put a d prime over 2. So now we will say this is 1 minus, and now we'll have d prime over 2 squared. And that's going to be good for d prime between 0 and 2. And of course, I like to be thorough here. It's going to be 0 whenever d prime is less than 0. It's going to be 1 whenever d prime is bigger than 2. So now we've got the CDF. Now we can get the PDF. So we're going to get the PDF for d prime by taking the first derivative. So we'll say d prime now of the CDF here. And now I'm just going to take the first derivative here and just do it, pretty slowly. And you will see that you get, let me just do it again. We're going to have the minus 1. We'll bring down the 2. Then we'll have 1 minus d prime over 2 taken to the first power, and then we have a minus 1/2 from the inside. So we pull all of this together, and this will end up just being 1 minus, if you look here, d prime over 2. And that will be good for d prime, keep forgetting to put my units on here, between 0 miles and 1 mile. So this, in summary, is kind of what we need. Because if we want to figure out what is the expected value of d prime, and you know how to get that, right? You just do an integral over, well, I'm going to let you do it. You should know how to do that. So I want you to verify that this ends up being 2/3 of a mile. So you'll see a pattern here. When we just had a 1 mile strip of street, the expected value was 1/3. Now with a 2 mile strip, we have 2/3. When the variance was just a 1 mile strip, we had 1/18 miles squared, and you should verify that this ends up being 4/18 miles squared. So I would like you to do this. You should verify, especially if you're feeling rusty with this stuff. So what are we doing? I'm trying to develop a method here that you can follow. So first we did it for a 1 mile strip, then we did it for a 2 mile strip. Now what I want to do is I want to make a general equation for a strip that is as long as we want it to be, all right? And that is what the next slide is. So for a distance between an accident and an ambulance on a line that is, or I kind of wish I had updated these slides a little bit better, but that's okay. General equations for my random variable d, which again is going to be the absolute value between my accident and my ambulance on a line or a road, whatever you want to call it. I'm going to make it just a miles long in this case. We'll use miles again here, okay? Miles here. And then one of these stars could be the accident, one of these stars is the ambulance, or the opposite here. And so you can develop this, and you can see that it is a general equation here. And again, I think you should probably just go ahead and try this yourself, but you should be able to get that the CDF for the distance between these two just by doing the same thing. In other words, you could define a new random variable like as follows. Call this, we could call this, instead of d, let's call it d new, all right? Let me just kind of set you up here. So I have a new random variable here. Every time you see a capital D, it's going to be d new, all right? Right here, and d new here. And what you're going to do is the same thing I did on the previous slide. You're going to say, okay, d new is just equal to a times the first d that I used, all right? And then you're going to go through that variable substitution. When you do that, you will end up with the following series of equations. So you'll have the CDF of d new, and it will have this form for d between 0 and a, and of course it will be equal to, I have to do this, it will be equal to 0 whenever d is This should probably be d new too. All of these little d should be d news. Let me write that in there just so I'm consistent. Hear my kitty cat? He is meowing. Here we go. Meh. Okay, I like this. This is also a d new. Well, you get the idea, I think, right? Okay, so when d new is less than 0, capital F is 0, and it's also equal to 1 whenever my d new is bigger than whatever a miles is. Anyways, you should be able to get to this, and what you'll find is that for any strip of road a miles long, it doesn't have to be a whole number, it could be anything, that my expected distance between these two random points on a road a miles long is going to be a over 3, and my expected variance, or my variance of that distance between the two, is going to be a squared over 18. So we're going to be using this. What I'm doing here is developing some relationships that we'll be using, and we're going to start complicating things. So like what we'll be doing eventually is, instead of looking at the distance between 2 points here on a road, now we're going to look at the distance between two random points in a grid, a city grid like that. So we're kind of developing, as I said, some protocols for that. Okay, so now we're going to, it says example 1 revisited. So here we go. Might use this for scrap paper. Hang on. First thing I need to talk about a little bit is Euclidean distance versus something called rectilinear distance or Manhattan distance. So I'm just drawing a couple of points here, and I've got the coordinates. I've got, just pretend it's a city, okay? So pretend this is a piece of a city, or a piece of my neighborhood. Actually, my neighborhood is probably pretty close to this. So we have, here's 0, and this is 4 miles in width, and this is 2 miles going this way. And suppose I just pick two random points. So I've got 1, 1, and 3, 2, and just because I'm going to need it eventually, this value right here, this is going to be, where is x? X is at 3, and it's at a height of 1. But the points I'm interested are in A and B. There's a thing called rectilinear travel. We also call it Manhattan travel or Manhattan distance, and they call it that because the streets in Manhattan, and certainly in a lot of other cities, if you want to get from point A to point B, you have to do a series of this, 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 this. So you go in a pattern of X and Y direction. Euclidean distance is the straight line distance between two particular points. So whenever you see the word Euclidean, think of it as just the straight line, like as the crow flies, as they say, or as a plane might go, for example. So what's the Euclidean distance between A and B? So we're just going to use what this c squared equals a squared plus b squared. So to get c, I'm going to get, because it's a triangle, right? So I'm interested in this value here. So I'm going to call this value A here and this B here. I'm just going to use, my geometry. And then this distance here is going to be C. And so I can see that the Euclidean distance between A and B is C, and I'm going to get that by taking the square root of this distance A. So what is that? I've gone from x is 1 to x is 3, so that's, I'll just do it this way, squared. And then my y change, I went from y is 1 to y is 2. And you can see that this is just going to be 2 squared plus 1 squared, so c is going to be the square root of 5, and that would be miles right there. But the rectilinear distance, now I jumped ahead of myself, is just going to be the distance that I traveled, and this is the absolute distance here. I went again from 3 to 1, which is a 2, and I went from 2 to 1, which is a 1, and now we have 3 miles here. Right there. Okay. Some values here. If they are independent, so on the next slide, I'm going to let the distance between these 2 points now that are on this in this community that is 4 miles width by 2 miles height right there. D is just going to be the absolute distance between x1 and x2. So remember, this is point A and this is point B, and this point right here, that was 3, 1. And so we could think of this, if you'd like, as this point A here might be, say, the location of the accident, and this might be, don't do that yet, this could be the location of the accident, and then this could be the location of the ambulance. So we could call this x1, y1, and this one is x2, y2, or vice versa. This could be x2, y2, x1, y1, and they could be, you know, anywhere here. So now what we've got is a little bit of a complicating factor in that now we have a two-dimensional surface area that we're interested in, and we are going to assume that we have the x values, so the 2 points, that x1, y1, because those are random variables, and x2, y2 are independent. Which means that each of their coordinates is going to be independent as well. So you should be able to determine on your own if we're doing what we call this rectilinear travel, or again Manhattan distance travel, that the expected value of D is just going to be the expected distance between x1 and x2, the absolute value, plus the expected distance between y1 and y2. And for this particular problem, you can see that if we have right here, this is going to be a continuous uniform random variable. So we're going to say that, I'm going to put that over here, that x right here has the continuous uniform PDF on 0 to 4 miles, and y, my y coordinates, are going to have the continuous uniform PDF as well, and they're independent, and that one's going to be on 0 to 2 miles. And so we know that for a continuous uniform PDF that the expected value of this rectilinear distance, what we're going to do is draw upon what we just determined. So this was the same thing in the previous slides up here. Recall that we determined that the expected distance, which is just the absolute value of two random variables, right? We determined that the expected distance, if we had a street that was A miles long, that was just going to be A over 3. So in this case, our A is a 4, and in this case, our A is a 2. So the expected rectilinear distance then is just basically saying what is the expected distance in the x direction plus the expected distance, in the y direction. And because these are things that we just developed, we know that we just have to take, for the x direction, we have 4 over 3, that's that A over 3 up here, plus we have 2 over 3, and so that gives us 6 over 3, and so the expected distance there is going to be 2 miles right there. So the variance of the distance between A and B then, how can we get that? Well, that's just going to be the variance, because they're independent, the variance of the distance in the x direction plus the variance of the distance in the y direction. Whoops. And again, we determined that for a street that is A miles long, that the variance on that absolute value difference, same thing, I probably should have written it out this way. I should have done it this way. I should have done it like this. x1 minus x2 plus the variance of y1 minus y2, and again, that's absolute value. We know that that's going to be a squared over 18. Now, because these are independent, that means that my variance in the x direction, that's going to be a squared, which is 4 squared over 18 plus. Then we have 2 squared over 18, and that will work out to be 16 plus 4, which is 20. 20 over 18, which we could turn into 10 over 9, and that will be miles squared. And we're going to be using that in a later lecture. Okay, we're going to switch gears here just a little bit. I know this is a longer video, so you might want to take a break right here. But I kind of wanted to keep all of this stuff from section 3.1 together. So now what we're going to do, again, I'm just developing some stuff that we're going to need later. What I want to do now is I want to look at, we're just going to look at this, pretend it's not even a street, okay? We are just going to look at the expected value of the minimum of 2 random variables on a line, okay? So well, I guess we are doing a street now that I look at it. It says a 1 mile stretch. I'll use orange this time. So now I'm going to take 2 random variables across a 1 mile highway. I'm going to let m be a new random variable. It's going to be the minimum of those 2 values. So capital M is the minimum of x1 and x2, and I want to determine the expected location of that minimum. So if I were to draw, I guess I'm going to draw my street again here, right here. All right, and this is 1 mile, and this is 0 miles. And let's just pick 2 points. We've got right here, we could have x1, x2, or we could have x2, x1. And what I want to do is determine the expected value of the minimum. What are my steps that I'm going to do? First, so the first thing I'm going to do is I'm going to get capital F m of m. Then I'm going to take the first derivative of it, and I'm going to get the PDF of m, and then I'm going to use the PDF to get the expected value and the variance if I want it. So to develop this, what I want to do is, again, I'm going to show an x and a y axis here, and we're going to have this value m that is somewhere between x1 and x2. So bear with me for a second. What I'm going to do is I'm just going to pick a value of m to do a little demonstration and then develop this. Hopefully I can develop it well. Let's just pretend that m is equal to 0.70. I just kind of pulled that out of my ear here. And then I want to make a little bit of a table, because what I want to do is I want to use geometric probability here to determine my CDF, right? So let's go ahead and we'll just pick some random points here, x1, x2, and then whatever the minimum of x1 and x2 is. So we'll just pick a couple of points. So let's say we pick the first point, we'll just pick 0.3 and 0.8. So the smaller of those two is pretty clearly, 0.3. Then we'll pick another one. Let's pick 0.8, 0.9. And the smaller of those two is 0.8. Pick another one. How about, let's just pick 0.7. Let's put it right on 0.7 and 0.7. So the minimum is pretty clearly 0.7. I'm just going to do one more. Let's do a 0.5 and a 0.9. And that minimum is going to be a 0.5. So think of this as me like throwing darts right here, okay? So let's just look at where these points are. So 0.3 and 0.8, that would be somewhere, this is roughly 0.3, 0.8, maybe right there, okay? And then 0.8 and 0.9, if I plot that, that's somewhere like up here. And then ignore the yellow for a second. And then we have 0.7, 0.7, well that would be right there. And then 0.5 and 0.9 would be like right up here. So I can keep doing this, but let's take a look at what I'm looking for is, remember I want to first develop capital F M of M, and that's going to be the probability that the minimum of my two values is less than or equal to a particular value of M. So if this particular value of M happens to be a 0.7, then which of these points meets this criteria, right? So the minimum, so this would be my random variable M, and then it manifests as a specific value of M. Which of these points meet this criteria? Well, is 0.3 less than 0.7? Yes, it is. So that was this one right here, right? And then how about 0.8? Is that less than 0.7? No, it's not. How about 0.7? Is that less than or equal to 0.7? Yes, it is. How about 0.5? Is 0.5 less than or equal to 0.7? Yes, it is, and that corresponds to this point here. Let me pick one more point just for S's and G's. 0.1 and 0.3. The minimum is 0.1. Is 0.1 less than 0.7? I keep doing this, I don't know why. 0.10. Yes, it is. So this would be one of the points that I am interested in here. So that gives me 4 points. We have 0.1 and 0.3. That would be like right, kind of right there. So basically what I'm trying to show, if each one of these points is a dart, is that all of the points that fall in this region right here, this is the area where the minimum value is less than or equal to that pre-specified M, and as I said, I just grabbed 0.7 there, all right? So if I wanted to use geometric probability to get the CDF of my minimum value, what I could do is look at all of this orange area here that I did here, we'll do it this way, over 1 squared, or 1 mile squared. So if these were miles, and I've been using miles here, so 1 square miles, or 1 mile squared, I should say, right there, okay? So what is this orange area? There's a couple ways I could do it, right? Let's just go ahead and do it by looking at 2 different rectangles here. So I'm going to add that rectangle and this rectangle. So what would that be? The area of this rectangle is 1 by M, so that's M, plus this rectangle here, it is at a height of M, and its width here is going to be 1 minus M. And so we could say, and this is again the functional part of my CDF, that if I gather all of my terms here, I'm going to have 2m minus m squared. And that is going to be good for m between 1 and 0 miles. And again, it'll be 0 whenever m is less than 0, and it'll be 1 whenever m is bigger than 1. But we could also have gotten it this way. If I look at my yellow area, and let me just kind of put that over here, just to do a little OR here, I could have looked at Fm of m could be 1 minus this yellow area divided by that 1 mile squared, right? So if I do that, I would get 1 minus, and what's the area of this yellow? Well, it's a square actually. Well, this piece here is 1 minus m, and this piece here is 1 minus m. So I would have 1 minus m squared, and lo and behold, that actually works out to be, if you do the math, watch, 1 minus, and then you'll have 1 minus 2m plus m squared. And what does that work out to be? It ends up being 2m minus m squared, which is exactly what we got the other way. So there's a couple ways to skin that cat. Okay, what are we trying to do here? Holy cow, we've lost our balance. EM, I want to figure out the expected minimum of those two values. So now what I need is, I'm going to get the PDF of m by taking the first derivative of my CDF in the functional region here. And I'm going to find that that gets me, where am I here? I'm going to get 2 minus 2m, and that will be good for m between 1 and 0. And from that, and I'm going to ask you to verify this, the expected value will end up being 1/3 miles, and the variance ends up being, it's kind of interesting, we've got some similar results here, although for a different application, and the variance is going to be 1/18 miles squared. And I'm going to ask you to verify that and that, okay? So now what do we do? Again, if now we have a highway that is now a certain length. I used A last time, I'm going to use S this time just to mix it up a little bit. So now I'm going to have a highway. I've run out of cool colors here. Let's do brown just for something different. So now I've got two random variables, but now we have a highway of S units in length, or S miles. Again, I used an A last time. I don't really care what you do. But now I'm going to call M prime is now going to be the minimum of x1 and x2, and I want to determine the expected value of M prime. So now, just to draw my picture here, we have 0 miles, and here we have S miles. That looks like smiles, but, and then we're going to have an accident and an ambulance, or an ambulance and an accident. Doesn't really matter. You could look at it that way, or just two random points. I'm going to do the same thing, only now when I draw my area here. Do I want to use M prime here? That gets really messy, doesn't it? Let's call it, no, it's fine. We'll just call it M prime. So this will be M prime, this will be M prime, this is 0, right here, this is S in miles, this is in miles, and this is S. So how can we get the expected minimum of 2 points over a S mile area? So I'm going to do the same thing. I'm just going to use a variable substitution. So in this case, I'm going to let M prime be equal to S times my original M. And so now I want to get capital F of M prime. We know that that's going to be the probability that M prime is less than or equal to that little value. I'm going to substitute and get the probability of S times my original M less than or equal to M prime. And then I can see that that's just going to be the probability of my original M less than or equal to M prime over S. And I can see that that's just capital F M evaluated at M prime, M prime over S. And just to remind you, what was capital F of M prime? That was from the previous slide, so just to remind you here, at 0 whenever M is less than 0, and, oops, hang on a second, I want to make sure I don't miscopy anything. And that was 2m minus m squared for 0 less than m less than 1, and 1 whenever m was bigger than 1. So now we're just going to take this function here and plug in m prime over s. So we'll get 2, where is it here? We'll have 2 times m prime over s minus m prime over s squared. Yep. Like so. And let me see here then, so that will be capital F of m prime. Make sure I copied that down right. I believe I did. Now I want to get, again, it's going to be 0 whenever m prime is less than 0, and it will be 1 whenever m prime is bigger than s. Now to get the probability density function of m prime, we're going to take the first derivative of this, again with respect to m prime, so that's going to get me 2 over s minus 2 m prime over s squared, and make sure I did that right. That seems right. And that'll be good for m prime between these two values here. And then I'm going to use this PDF to get the expected value of the minimum of the two right here. And that ends up being s over 3, pretty convenient. And the variance of the minimum of the two works out to be s squared over 18. So a very similar result when we were just looking at the expected value, same result, of the distance between 2 points, the absolute value. Now, I'm going to ask you to do something, and it's pretty cool. I want you do this. You do this. I want to know what, or I'll say this, show that. I'm going to define a new random variable. Hang on a second. That for, I'm just going to use L, okay, for large. L is a new random variable. L, the maximum of 2 random variables, independent random variables, same as these here, so both continuous uniform, okay, same idea. So I want the maximum of these two, and I'm going to call it L. So for L, the maximum of 2 independent random variables on 0s, that the expected value of the larger of the two will end up being 2 times s over 3. You can hear my cat puking in the background, I bet. It's so gross. And that the variance of L is equal to s squared over 18. And then if this was miles, I guess this would be miles, and this would be miles as well. And I'm going to suggest that when you do this, you just follow the same way that I did it here. You know, start it out so you can learn this. This is fair game for quizzes and exams, so make sure you can kind of understand it and follow it. If you can't, throw up a question on Piazza, and we'll help each other with it. But I'd like you to do this, and because you'll get a lot of confidence about your abilities by doing that. So sorry for it's a bit of a long lecture today, but sometimes we have to do that. See ya!